Hi to everybody, my name is Elena Zucca and I am presenting this paper which is about a big step from finite to infinite computations. So the main motivation for the work is that, as it is well known, in big step semantics we have no explicit modeling of divergence. Non-terminating computations are just identified with stack computation. In both cases we derive no judgment. This is not good. It is the reason why, for instance, to prove soundness of a type system, we usually adopt small step semantics. And it is even worse in case of observations, which means when we have that a non-terminating program may have significant semantics, for instance, because it makes input and output operations or other effects. For this reason, the aim of this paper is to define a construction, so a general construction, which, given an arbitrary big step semantics represented by a judgment like that, where we have that a configuration C evaluates to a final result R, producing a finite observation O, and this defined as usual by a standard inference system interpreted inductively. So starting from this judgment, we canonically extend the semantics to a richer judgment where we have R infinity, which means either a final result or divergence, and O infinity, which means a possibly infinite observation. The key idea is that to define this judgment, we use a recently introduced framework, which are inference systems with co-rules. The main idea is that the judgment is defined co-inductively, which means allowing infinite proof trees, but we have a special kind of rules called co-rules, which are used to allow only some of those infinite proof trees, and so they allow to refine the co-inductive interpretation. I will illustrate the idea on an example. It is just lambda calculus, where we only add an expression out E, which, as you can see in the rules, has the expected effect that the value of the expression E is evaluated, the value V, and the effect of this output expression, apart from returning the final value, is to add this value to a sequence O, which is a sequence of values, so it is a finite observation. Okay, so it's quite clear that with this definition interpreted inductively, we only model finite computations. So, for instance, no judgment is derivable for omega, which is the well-known out application which diverges, and this could seem not so bad, because in this case we have that the effect of the execution is that there is no visible observation because there is no output, but the same happens for this other term omega hat, which is the same of omega, with the difference that every time the term omega lowercase is applied to itself, we also add to the output sequence an instance of the term. And so in this case, the observation produced by the evaluation of this term is an infinite sequence of omega lowercase. This is what we expect. So how to model such infinite computation? A first step, first quite natural idea, can be to add to the results a special result denoting divergence, infinity, and to extend observations from finite sequences of values to possibly infinite sequences of values. A second step, also quite natural, is to add rules for divergence propagation. The basic idea is that for each original meta rule, we also take into account the possibility that one of the premises diverges, and so what happens is that the consequence should diverge as well. For instance, for application, we have three rules, and for instance, in the second rule, we consider the possibility that E1 converges, but E2 diverges, and so the application should diverge. The third and most important step is how should we interpret the set of rules. Of course, if we take inductive interpretation, we will have no judgment for diverging expression, which should allow infinite proof trees. However, if we allow infinite proof trees, we will have too many judgments for diverging expressions. For instance, for the omega term, it is easy to see that we will have an infinite proof tree where omega can evaluate to an arbitrary value and an arbitrary observation, because we can construct this tree for any V infinity and O infinity. So, which is the role of corules? We add these two corules. One is counit, which in the consequence has the empty string, which represents the absence of observation, and cogen. Cogen actually is not a single rule but a pattern. So there is one such rule for each original rule which generates an observation. So in this example, the only one is the rule for output. And so what happens is that the corule generates an arbitrary, possibly infinite observation where the initial prefix is the one generated by the corresponding meta rule. So the role of corules, which as you can see are indicated by the thick line, is that an infinite proof tree is only allowed if each node has a finite proof tree in the inference system where we consider both rules and corules. So corules only allow infinity as a result, and so it is easy to see that they only allow infinite proof tree where we have infinity. For observation, they have a different role. In particular, rule counit is used in the cases where we have a finite observation in the computation. So, for instance, in the omega example, the empty sequence, because in this case we have an infinite proof tree for any observation with the prefix O, and the role of the corule is to only allow the case where the continuation of the observation is the empty string. On the other side, the pattern cogen is used in the case where a computation produces an infinite observation, like in the case of omega hat. In this case, the observation is uniquely identified. For instance, in this case, we get the unique possible solution of the equation induced by the proof tree is, as expected, the sequence of the infinite sequence of values which are the term itself. And so in this case, the corules should allow a finite proof tree for any node generating an observation, so it is enough to add a corule for such nodes, so for the meta rule which actually generate an observation. So let me briefly explain how from the example we go to a general construction. We have a general definition of what is a big step semantics, where we have a judgment with configurations, results, and observation. And the key point is that observations are modeled in a general way by a monoid, where we have a composition operator and a unit which represents absence of observation. This is the monoid for finite observation. We also have a set of rules with a non-empty set of premises, and for results we assume to have just a standard axiom which says that the result evaluates to itself and to the unit observation. For the rules we have that the result is the result of the last premise, and the observation is constructed composing the observations of the various premises plus O, which is the observation actually generated by the rule, which of course can also be the unit one, so no observation. Okay, given that, we have that to go from finite to infinite observation, we pass from the monoid to an omega monoid, which is a new kind of structure, where we have a possible infinite observation, and we also have a mixed product. Besides the product of the original monoid, we have a mixed product which combines finite with possible infinite observation, and we have an infinite product which transforms an infinite sequence of finite observation in a possible infinite one. Then for the second step, so this was the generalization of the first step. For the second step, as we saw, we add a rule for divergent propagation for each original meta rule and for each premise, which models the fact that each premise can also diverge, in this case the consequence diverges as well. And for co-rules, the third step, we have the co-unit, where in general we have the unit element of the monoid, and for each rule where the observation is not the unit, so it is relevant, we have a corresponding cogen rule where we allow each observation whose prefix is the one of the corresponding meta. Okay, so results. So now very briefly some results of the paper that I have no time to describe in details. So first of all, in the paper there are many other interesting examples of big step semantics which differ for the monoid of observations. So here in this slide you have the various monoid of observations and the corresponding omega monoids. So for instance, if we can generalize the example of the lambda calculus to have sequences of events, such as I/O events or whatever, and they generalize, of course, to possibly infinite sequences. We may have costs of events, which are modeled by a monoid where we have a real number with plus, and they are in the omega monoid, they are extended with an infinite cost. We have a monoid of where we have finite power set which extends to the full power set, and the natural number with join which also are extended to adding an infinite value. So depending on the monoid of observation, we should add only the co-rule, co-unit, or both to get the wanted, the desired behavior. So indeed we have a theorem, many theorems actually, of correctness, and the idea is that to prove correctness of the construction we assume a reference small step semantics, and what we prove is that equivalence with small step semantic is preserved under an assumption of determinism of the semantics, which means that if we start from a big step semantics which is equivalent to finite computation in small step semantics, by the construction we get an extended big step semantics which is still equivalent also to infinite computations in small step style. More precisely, we have these theorems, so denoting in this way the fact that we have a small step computation where O infinity is the observation obtained by composing by the infinite product all the observations of each step. We have that taking counit and cogen, we always have completeness. Taking only counit, we always have soundness. For the other cases, we need some additional technical requirement on observation, which I don't want to detail now. So, to conclude, the contribution of our work is a general construction which takes big step semantics and makes explicit also the model of divergence in these semantics. This construction can be applied to a wide class of definition, as we show by many examples. As a side product, we also have a new notion, a new structure, a notion of omega monoid, which nicely models finite and infinite observation, and an abstract framework modeling what is a big step semantics, general enough to capture very interesting and different examples. As future work, our main goal is to improve the construction, to remove the assumption of non-determinism, which is currently needed to make the correctness proof. Okay, that's all. Thank you, and if you have questions.